Okay, now today we'll look at a new chapter, chapter 7. So we'll look at a heat transfer and mass transport. Basically is related to thermodynamics. So we look at 3 items in chapter 7. Basic, we look at equation, and then we look at how we solve it using finite element method. And we will only limit to 1D and 2D heat transfer problems. Okay. All right. Now, when we talk about heat transfer, right? Heat transfer, we will look at derivation of equation first. So when we talk about heat transfer, bear in mind that we are talking about energy. Okay, we bear in mind that we are talking about energy. All right. If you look at the screen, you have a picture on your left-hand side of the screen. You're having a cube, right? You're having a cube. And the heat is transferred from the left of the cube and then come out from the right hand side of the cube. So in this case, our heat flux, or you can assume this one as a heat energy. We write as a Q symbol, small q. Small q is a energy per unit mass. But anyway, you see it as a energy. Energy coming from the left, come out from the right. So we use as small q. Why there's a small x there? Because it is along x-axis. Okay, it's along x-axis. So we write as small qx. Okay, small qx. And then when it come up from another side, because the length of your cube is dx, so there must be something happen to the energy. So we write on the right hand side, when the energy come out from another side, we write as q sub x plus dx. It means that x plus dx means is come up from another side. Okay, and in our case, we are only looking at heat transfer happen in this phase. Okay, this phase. In this phase, and then come out from this phase. Okay. All right. So you know that cube, you have 6 faces, right? So our heat transfer, when we derive equation, is only we look at the input and output surfaces. Input, and then another one is at the back there. Okay. Now what happened to other faces? Other faces we insulated, means we cover with something that the heat energy cannot dissipate. All the 4 faces at the side we cover with some material that it do not allow heat to transfer out. Okay, so we only focus on 2 surfaces, which is on the left and right, and then the 4 surfaces at the side are insulated boundary, means the heat cannot go out. Okay, so this is a very important concept for heat transfer. Okay, so when we derive, we only have 2 surfaces that conduct energy on the left and on the right, and then the other 4 surfaces, they are insulated. Okay, any question on the diagram? Stop me if you don't understand what is happening on the screen here. And then what is the Q, the big Q? Q is the energy inside the cube. Okay, energy inside the cube. A means area. Okay. All right. So the diagram that you see is happening in the heat transfer happening in one dimensional. One dimensional means one direction only. Okay. So in the previous axis, or in normal 3D dimensional, you have x-axis, y-axis, and z-axis. So if you are solving one dimensional, mean you are only focusing on one directional. Okay, and the side is insulated, means no heat transfer at the side of the cube or on the object itself. All right. Now in this chapter we focus on two shapes only. One is cube object. Sorry for my drawing. Another one is round object. Okay, or cylinder objects. So we focus on two. All right. What is the difference between these two? Is the area. A, this one, will be different. So if you are using a rectangular object or cube, means your area is you times the side lah. Okay. Maybe I write this one is A times B lah, if you want to calculate the area. However, if you're looking at cylinder, you're looking at circle area, the A become pi r square. Okay. So these are the difference when you talk about chapter 7 about heat transfer. All right. Now we derive the equation under without convection. Now you know that energy can transfer through a few mechanisms: conduction, convection, radiation, right? So in this case, we assume our system do not have convection, right? Only happen at conduction. Right. So we start derive heat conduction without convection. How we start? We focus on energy. Again, heat transfer is about energy. So how do we write? So on the left hand side is capital E, which is the energy entering the control volume. This one on the left, energy that we supply plus energy generated. If you have energy inside here that can generate it itself, let's say you have a radiation object that can generate heat, right? Or a chemical that can generate heat, then you have some entity here. Means you need to include the energy generated from inside. Okay, so on the left hand side is your input. So energy in, it is the energy entering into our control volume. In this case, we have a cube. All right. The unit of E is in joule. So energy is in the unit of joule. So this is a unit that you need to focus when you come to chapter 7 for heat transfer. Okay, unit is joule, or capital E. On the left hand side also joule. So on the right hand side, what does it mean by U? U is a store energy. All right. And delta U is a change of store energy. So anything changed to the inside store energy, then you put it on the right hand side. Plus what is coming out. Okay, so this is an important concept. You focus on input, you focus on generated on the left hand side, and then on the left hand side. On the right hand side, you focus on store energy and the energy coming out from the control volume. Okay, quite direct, right? So E in plus E generated equal to delta U plus E out. So what is in will equal to what is out. Next, I'm going to give you a little bit more detail. How you calculate the energy that entering into control volume? You take Qx. Qx is the heat flux. Heat flux in the unit of kilowatt over meter square. Heat flux. And A dt. You times Qx times A times dt. All right. A is the area, dt is the change of time. All right. Then the energy generated you can write as Q, capital Q, which is the heat, capital Q times A dx dt. This is for the energy generated inside the system, inside the control volume. Okay. Delta U is the stored energy, changes of stored energy in the unit of kilowatt hour. All right. So this one usually you will be given delta U. And the energy out means you take what is happening to your Q. Again, out on the left hand side, your Q become Q sub x plus dx because it's going through some dx here. So your Q x plus dx is on the left right hand side of the control volume times the A and dt. So this is the second equation for today. First equation is the general concept, how you derive the equation by using conservation of energy, in equal to out. Okay, in equal to out. On the input side, you have energy entering from the left hand side plus the generated inside generated energy. On the right hand side is what is coming out, E out, plus the change of internal energy, delta U. And then you can see the equation on the second equation that you see on the screen here. Right. So far, okay, yeah? So far, everyone all right? Okay, I'll continue. All right, the rest you can read from the slides here. So we have two equations on the screen here. One is the general concept, and then another one is a more detailed with the Q A dt parameter. Next, we're going to introduce you Fourier Law of heat conduction. I think this one you learned in your thermodynamic class. Fourier Law of heat conduction, meaning every time you see a conduction case, excuse me, your Qx can be calculated as negative Kxx times the temperature differentiation. Negative Kxx dt over dx. This is capital T, which is represent temperature. Okay. Kxx is the thermal conductivity. Y in x. Why you see a x there? Because it's in x direction. Okay. So what does this Qx important? Because this equation is to calculate this Qx. Right? Same concept if you want to calculate this one, meaning you're focusing on the right hand side. All right, means you this one on the right hand side means you're focusing on the change of temperature over here times the distance of x plus dx. Right? So the third equation that you see today is a Fourier law given you an equation how to calculate the Qx. Qx equal to, again, negative. Negative Kxx. This is another equation that happened on the right hand side area. To calculate the Q sub x plus dx, which happen to the right hand side, the heat flux that come out from the control volume, given you again negative Kxx. However, we look at boundary condition at the right hand side, x plus dx. we still at Fourier Law under conduction. Again, heat transfer, we have three common mechanism: conduction, convection, radiation, right? So we are now at conduction. Okay, conduction, you use this equation. Q equal to minus kxx dt over dx. All right. And when we derive equation for this module, for finite element analysis, we will use the famous Taylor series. You've seen this one before, right? And we limit to only two terms, or power of 2 in the equation. So you see something like this. So when you expand this qx plus dx, which is the q at the right hand side coming out, you will get negative, and then you have a negative kxx dt over dx plus differential d over dx minus kxx dt over dx and dx. So this is we only look at two terms inside Taylor series. Okay. So this is, again, there is a negative inside. Outside the equation there. All right. So have a look on your screen. Something changes, not changes, something expanded from Fourier Law, from a simple equation, then combined with Taylor series concept, we only limit to two terms, meaning the second term of the equation under Taylor series. So you will get this equation. All right. So if you're interested to know about Taylor series, is fall under calculus. Under calculus, there is one particular chapter that that talk about Taylor series, right? When you learn about differentiation, right? So this is application of differentiation, right? Okay. Next, we have done with Fourier Law. Next concept we learned this morning will be the change of stored energy. The change in the stored energy. All right, I'll ask question to the class. Sue, are you there?
Yes.
So if you look at your screen, if you look at either the first one or second one, which one of these represent changes in stored energy? Which parameter here represent changes in stored energy? Is it capital E, capital U, or Q, small q? Definitely not A. Definitely not X, not T. So which one? Capital E or capital U?
Capital U.
Capital U, huh? All right, correct. The answer is the changes of stored energy. We are looking at this term now. Okay. We already explained how to find Qx, right? There's an equation minus Kxx. If you need to find the Qx, you use this equation minus Qxx dt over dx. But for the right hand side, you use this equation. Okay, for the right hand side, you use this equation. Now we look at delta U, which is the changes in stored energy. How you calculate delta U? You take specific heat times mass times temperature. specific heat, mass, and temperature, where you learn in thermodynamics is a Cm delta T. So specific heat here is in the unit of kilowatt hour over kilogram Celsius is a specific heat. So where can you find this C? This C can find in a table, in a material table, that normally you will find a specific heat for that particular medium. So steel, aluminium, titanium, all of it have their own specific heat. All right, now how do you find mass? How do you find mass? Just use a simple physics calculation. You take density times volume. Density times volume, density rho. So again, from the material chart, you manage to find what is the rho. Rho is the density times volume. How you find volume from the control volume? You take the area times dx, you find volume. Okay, logic, right? So far, everything seems logic to you, right? And then changes in temperature is dt. All right. So this is a concept to find changes in the stored energy, with this delta U, where you take specific heat times mass times temperature. Okay, change of temperature. So meaning you have temperature 1 over left hand side, temperature 2 at right hand side, meaning temperature at this surface, temperature 2 at this surface. You find the delta T in the system, then you substitute inside this equation. All right, now just a common question I'm going to ask. Is Brian here? Brian, are you there?
Yes, sir.
All right, now Brian, when you talk about conduction, right? Now conduction, I'm going to ask, you have temperature at surface 1, temperature at surface 2, and the heat flux happening from the left to right. What do you think the temperature 2 will be? Will temperature 2 higher than T1? I'll give you two scenarios. Will temperature 1 smaller than T2, or temperature 1 will bigger than T2? What do you think when it happen in conduction?
Temperature 1 bigger than temperature 2.
Correct. So just bear in mind, just bear in mind how to make the energy flow from left to right. It will be the same as the concept of pressure, right? So temperature or heat flux will move from high flux to low flux. Means high temperature move to low temperature. So just bear in mind in that. Okay. So by looking at the temperature, you know that the direction of Q, small q. So in exam, normally the arrow won't be given. So in exam, let's say you're given a 2D diagram. I give you the temperature 1. I give you temperature 2. So by looking at the temperature itself, you know the direction. If T1 is higher than T2, then Q is happening from the left, then come up from the right. So this is Qx, this is Qx plus dx, provided the length of this control volume is dx. Okay, just keep in mind, yeah. All right, very good. So we have done changes in the stored energy Q. Okay, so far what we have discussed, we discussed Qx, delta Q. Again, how you find Qx? By using this equation. Fourier law, Qx equal to negative Kxx, differentiation of your temperature. Okay, minus Kxx dt over dx. And on the right hand side, if you want to calculate the right hand side Q, you use this equation. Qx equal to dx minus n, the one that you see on the screen here. Right? So for chapter 7, for this chapter, you have to recall back your differentiation skill, because as you can see from the equation on the screen, they are differentiation equation. Okay, so you need to recall how to do differentiation. Your temperature will be given in the equation, so you have to be good in differentiation skill. Right. All right. Next, you substitute what we learned in previous slides. You substitute all the K value and the C value inside the second equation here, and then you divide, you take out the A dx. You divide with the equation with A dx dt, meaning you take out both sides with A dx dt, you divide. Then you rewrite, you will get as partial differential or delta d over dx, kxx del t over dx. This is partial differential. Partial differential means very small changes, right? Plus q, because this one already divided by a dx dt, plus rho c delta t, and this one is removed, right? Because when you rewrite, you can cancel each one, right? So you will get this equation, the one that in the light blue color. Okay. All right. So the equation that you see on the screen here is important when you want to solve one-dimensional heat transfer under conduction scenario. You write del over del t, kxx del t over dx plus q equal to rho, this density, rho c specific heat del t over del t, right? Temperature over time. Right? We will discuss one tutorial question about this one later. Okay. So far, any question on the equation? Anything you want to ask me about the equation? If good, then I move on, yeah? All right, I move on. So, I changed the three-dimensional diagram into 2D now. So as you can see here, on the left-hand side, the diagram, you will see I denote as temperature on the left-hand side, or there's a B there, means base. You can see that the object is mounted on the wall. Okay, mounted on the wall. So I represent the temperature at this location as TB, and I label this one as S1. All right, as S1, and then the length, and you have the QX. You have the QX equal to plus QX star, I will explain later. And positive x direction is to the right. And you have the S2 on the left hand side. Right? Okay. So these two diagrams, what are the differences? Is that one is with isolated, one without isolated. So it means this one on the left hand side, you have something happened on the left, something happened on the right. However, on the second diagram, because it's insulated wall on the left hand side, so straight away you write your Q star equals 0, meaning you don't have any heat transfer on the left hand side. And yeah, and then the rest is just your temperature and your S. Okay, let's look at what is the equation. So this equation in light blue color is what you see from our derivation just now. So you have partial differential del over del x, kxx del T temperature over dx plus q equal to rho c del T over dt. Again, we are looking at one dimensional, which is in x direction only. Why in x direction only? Because our control volume is insulated at four corner of this four corner was sealed by something that cannot allow heat transfer to the side. So your heat transfer only happen from the back into the front. So you only have two surfaces that do the conduction. So that's why in your equation you are seeing x only. We are looking at steady states. So when you steady state your mathematics equation, you can write equals 0 on the right hand side, meaning there's no changes of your temperature at the right hand side. Okay, so when you do differentiation, if you have a steady states, means the differentiation mathematic model, when you do differentiation, it will equal to 0, right? Or more recognized term is that especially when you have something deal with time, in this here on the right hand side, this term will equal to 0. Means there's no more heat transfer. What does it mean in steady states? It means the temperature will be the same. Okay, will be the same from on the right hand side. Okay, let's say this is your heat transfer. This is out. This is your Qx. This is your in. This is your output. This is your Qx plus dx. What means if you see a steady state means temperature at 1 same as temperature at number 2. So no more heat transfer happen. Okay, just let you know the concept. Another term where you can take out the d over dx is that when you have a constant thermal conductivity and steady state, then you can take out this dx. Okay, you can take out this dx in the mathematics equation. Okay, this one only steady states. However, the third equation here is steady state plus when you have a constant thermal conductivity, then you can take out this d over dx means right in the equation. All right. Now we focus on constant thermal conductivity and steady states equation, which is this one. I will go to the top of the screen. We can write equation on the left hand side of your screen. The boundary condition, meaning what happened to that particular point. So at this point, we call it as S1. Okay. S1, S means surface. At surface number 1, we have our temperature equal to temperature at these boundaries. Label as T sub B. Okay, T sub B as 1. And we can write the equation at surface number 2, which is here. This surface number 2. What happened to our Q flux? Q flux is Q star X means is a prescribed heat flux, or you can just see as a heat flux at particular location. Okay, in this case, we just want to separate. There's something changes to the Q flux, the Q. So we just denote as there's a star above the Q there. All right. In this case, we draw a free body diagram here, and at surface number 2, or at a certain location after the certain length from surface 1, okay, we write our Qx at these surfaces as Q star X. And we use the equation of our Q that we learned just now, 10 minutes ago, or 20 minutes ago. Q equal to negative Kxx d squared T divided by dx squared equal to a constant. Right. So if you have insulated boundary, like this case, if you have any surfaces that is insulated, in the question, if you see any insulated surface, means there's no heat transfer happen. So the area will be 0. What does this mean? If I draw a cube, and the 4 surfaces of the cube is insulated, meaning all these surfaces, this surface, you can write Q equals 0. Small q, heat flux is 0 because there is no heat coming out. These surfaces also, Q equal 0. Okay. Or you can write, this one is top lah. So Q top 0. Q side, maybe this one side 1 equals 0. However, we are looking at there's one particular direction with this. There's an in and out of your heat flux. Q in with a label as X. This one out, X plus dx. Okay, assume that this is your X direction. So this is what happened. Okay. What meaning by positive Q here? Explained by this statement on the screen. When you have a positive Qx with a star, there is a heat going into the body. Okay, there's a heat going into the body, or every time you see a Q with a positive value, when you draw your free body diagram, the Q is always pointing into the surface. It's a Q. Right? The arrow always pointing in when you have a positive Q. Pointing in to the surface when you have a positive Q. Okay, so just take note on this one. Okay. So we have done with the one-dimensional heat conduction without convection. We'll go for a short break and we'll look at two-dimensional, where the heat transfer will happen in Y direction. Okay, we already completed explanation on one-dimension heat transfer under conduction mechanism. which is in X direction. After the break, we will come back and look at two-dimensional in Y direction and X direction. Okay, I stop the recording.